Hi, this is Wisewell. We're talking about the AP Summer Assignment. Thank you for tuning in. I put up this assignment on a link. Let me make sure you can see the link. The link is bit.ly. I'll put a lot of links up there over the course of the year. Mr. W, and this is AP Summer. That's a link to this PDF, and the link to this video is bit.ly Mr. W AP Summer, and I think I put a SOLN on the end for solution, but there's no gap there, so let me just do it a little closer so it's clear. AP Summer Solution. So welcome to AP Physics. Glad you're here. Let's get started. There was some information here to read. We're talking mostly about the math skills you'll need for the class. You know this stuff, don't worry about it. But just let's make sure that it's top of your mind, right? That you can still do it. Complete your work on the pages provided. Calculators should not be used. So that's to say this isn't that hard, but also you should know some fundamental arithmetic. Your work must be legible and linear. Mark your final answers by circling or boxing. This is a good practice. We'll emphasize this in the class. When you get your answer, for instance, just put a box around it. And DFU. Don't forget the units. I guess we already missed this deadline, but please turn in this work. This is your first grade in the grade book. I already put the assignment in, so I got the schedules for you for my classes, so you're in my class until you drop it, I guess, or until you finish it. And this is your first grade. You know, the funny thing about copying is you're only hurting yourself. I'm not going to track you down and figure out exactly what you copied or didn't copy. You know, it's always a good idea to give credit. So if you just put down, you know, worked with, say, Adam or something, put that down and we will be good. All right. You don't need physics for this. You don't need physics for this packet. I'd like you to get 90% or better. That's why I'm making this video. If you don't get that grade right away, I can let you redo it. So don't worry about that. First thing we need to talk about, so let's get started. First thing we need to talk about, significant figures, scientific notation. So when I write 6.02 times 10 to the 23rd, also known as Avogadro's number, I'm using scientific notation. That is, this is the decimal part and this is the power of 10 part. It's 6.02 because there are three sig figs, significant figures. Sometimes we abbreviate them sig figs. 3 decimal places, even though there's a 0 in there, that's still significant. It turns out anything after the decimal point is significant if there's a number after it, or if there's a number and then there's zeros after it. So for instance, this number has 2 zeros here before the 8 and then 2 more after those zeros, but it's all to the right of the decimal point. So the rule is zeros to the right are not significant unless you have a number there, or unless you really made some effort to write it down. So this is the rule. Zeros to the right of decimal aren't unless you emphasize them. What do I mean by emphasize? Well, I could have just written 27, that would be fine, but when I put a 0.00, I have 4 significant figures in that number because I know the 2, I know the 7. Imagine on a ruler you had 26 and 27 and 28. What you're doing by saying 27.00 is like that measurement was like dead on 27. The significant figures for pi are unlimited. You can put in as many decimal places as you want. In other words, pi will never limit the number of sig figs in your answer. So if you've got the circumference of a circle equals 2 times pi times the radius, there's unlimited digits of precision for 2. There's unlimited for pi. So really the answer depends on how well you know the radius. If you only know the radius to 1 meter, and I tell you what, there's only 1 sig fig in your answer. If you know it to 1.05 meters, remember that's getting down to 5 centimeters. That's a little bit more precise. That's going to have 3 sig figs. This is also going to have 3 sig figs, 1.00, because it's way different, 1.00 from 1 meter all by itself. And 1.050 is even more significant yet, so that's 4 sig figs. Because I wrote down the 0. If I didn't know that 0, then I shouldn't have written it down. That's kind of the general idea. There's a rule then too. This is kind of similar to that rule. So this is 4 sig figs, right? The 6, the 0, 0, and the 1. Because if you could measure all the way down to here, then these other digits had to be significant as well. In other words, this is just a hair over the 6 on your measurement scale. This is an 8, but I knew the 0, so it was a little bit more. So this is 2 sig figs. Now, Mr. Weisenfeld, wait a second. I see 5 numbers there. Well, here's the thing. You can write this as 8.0 times 10 to the 1, 2, 3 times 10 to the minus 3. And if you write 8.0, you're saying something more than 8 times 10 to the minus 3. Do you see why there's 2 here and 1 here? Because in sig figs, you only had 2 digits on this one. Similarly, I knew 200,000. I knew I didn't have 210,000. I was less than 210,000. I knew I had 6, but then I had no idea where I was at. So, scientific notation helps us keep track that this is only 3 sig figs. If you wanted more sig figs, you would need to add 0 in the scientific notation. So 2.06, 1, 2, 3, 4, 5 times 10 to the 5. Remember, in scientific notation, real quickly, we'll talk about it here, but you have 5 is the number of times you have to move the decimal point to get back to like where the decimal point is normally when we don't have scientific notation. Okay, so we're good on number 1. I think this is 2, 4, 6, 8, 10 points. And that's not really the answer. The answer is, well, you get to the answer by writing it in scientific notation. That thing's not going to erase. So this is 3 significant digits, 3. And I got there by writing 2.06 times 10 to the 5. Okay. Next question. Find the following. Final answer should be in scientific notation with the correct number of significant figures. All right. 5 times 10 to the minus 8, 2.9 times 10 to the 2. Let me zoom in a little bit here. This is 2 significant digits. This is 2 significant digits. 2.9 times 5 is 9 times 5 is 45. Whoa. Times 5 is 45. 2 times 5 is 10. 14. 14.5. Right, 3 times 5 is about 15, right? So 14.5 times 10 to the minus 8 times 10 to the minus 2. So when you have 10 to the 1 times 10 to the 1, that's 10 times 10, that equals 100. So what you did is you did 10 to the 2. So you just add exponents when you're multiplying. So minus 8 plus 2 is minus 6. So this is 14.5 times 10 to the minus 6. And you only get 2 significant digits. So what you have to do is you have to hack that one off. So this is 14 times 10 to the minus 6. Oh, hang on, Mr. Weisenfeld. 0.5, I'm supposed to round up to 15. Well, there's another crazy rounding rule. Which says that if you have an even number, you don't round up. So, I'll accept 14 or 15 times 10 to the 6, but if you got 14, you're super awesome. Okay, next question. Let's go over to number 3 here. 3.25 times 10 to the 4th plus 7.4 times 10 to the 3. So let's see, 3.25 times 7.4. I'm not supposed to do this with the calculator, so this is going to be long multiplication. 4 times 5 is 20. 2 times 4 is 8. Plus 2 is 10. 3 times 4 is 12, 13. 7 times 5 is 35. 2 times 7 is 14. Plus 3 is 17. 3 times 7 is 21, 22. Add this. I have 3 decimal places. 1, 2, 3. So 24.050. So when you're multiplying, you only keep the lower number of significant digits. So I only get to keep 2 sig figs. So this is 24. I add exponents. This is 24 times 10 to the 7th, which is, pretty good answer. 2.4 times 10 to the 8th. That's an even better answer because you have one number to the left of the decimal, and then you can have 1 or more to the right of the decimal, but you basically have maxed out your powers of 10. So 2.4 times 10 to the 8th. And then let's do this one here. So 6, notice that this has 4 sig figs, but these both have 3. So when you're multiplying and dividing, you'll only have the least number, so 3 sig figs. 1 divided by 2 is 0.5, or a half. 6 times a half is 3, so this is 3. You add exponents across the top and then subtract across the bottom. So this is minus 11 plus 26 minus 7. So that's minus 18 plus 26. That's plus 8. So this is 3.00 times 10 to the 8th. So I knew that 6 times 0.5 is 3. I know that I need 3 significant figures in my final answer. I indicate that by putting extra zeros after the decimal point. I get my exponent by using my exponent rules. Okay, 84 divided by 12, 1.2 into 8400. What you do is you move this decimal point over. So let's see here. This is 12 into 84,000. This goes in 6 times? No, 7 times? 7 times. 7 times 2 is 14, 7 is 84. 0, 0, 0, 0. So that's 7,000. So 1.2 goes into 8400 7,000 times. But this is, yeah, I could do it that way. So now I have 7,000 divided by, so that's really 7 times 10 to the 3, right? Writing the answer, divided by 1 times 10, so times 10 to the minus 7. So remember, these positive exponents in the denominator, you can flip them to the top by making them negative. So this is 7 times 10 to the minus 4. Because minus 7 plus 3 is minus 4. Why is this such a small number? That's what I can't figure out. Well, take a look. This is 8,400, but this is 1.2. This is like 12 million. So 8,400 divided by 12 million is going to be a pretty small number. Here's another way to do it that I noticed while I was looking at it here. So this is also 8.4 times 10 to the 3 divided by 1.2 times 10 to the 7. 1.2, 8.4, that's 7. 3 minus 7 is minus 4. 7 times 10 to the minus 4. So you can do it piecewise. You do this divided by that, and then you do that divided by that. And when you divide, you subtract the bottom from the top. So 3 minus a 7 is a minus 4. Okay, so that's like 2, 4, 6, 8. That's another 8 points. And it has to be, yeah, I guess now that I look at it, this could be 1.4 times 10 to the minus 5. Has to be basically 14, I think, or I said 15, so or 1.5 times 10 to the minus 5. Just because of the rounding stuff, that was hard to read. Hang on a second. So I'll accept either of these answers. I need to indicate here that I have 2 sig figs, so I got kind of lazy. 2 sig figs means this is 7.0 times 10 to the minus 4. And that should have been down here too. remember, you indicate sig figs in scientific notation by putting decimal points after, by putting zeros after the decimal point. And this one has 3, so we're good there. Okay, so next page. Okay, follow the example of the centi and prefix. So centi is a 100th of a meter. This is a meter. And this is a 1. I mean, meters are, if you have 1 meter, it's just 1 meter. This is called a mu. This is mu. Let me put the name of the symbol over here. So the name of the symbol in each case is interesting because we're going to be using some Greek letters in the course. So the name of the symbol, this is a mu, mu, it's a Greek letter. N is nano. I guess I should write it over here. N is not the Greek letter, it's an English letter. Nano, so milli, no, that's not a meter, that's a milli. My bad. A millimeter is 10 to the minus 3, a thousandth of a meter. A micrometer is 10 to the minus 6. And a nanometer is 10 to the minus 9. So I just remember milli, micro, nano. If you remember that kind of pattern, I mean, I guess, yeah, you just remember milli, micro, nano, how it goes, and then you'll get it. Kilo is 10 to the 3, so this is thousands. Mega is capital M, mega, 10 to the 6th meters or kilograms or something. And giga or giga is 10 to the 9th. And there's exa and peta, tera. There's a bunch of other prefixes and things. So let's see. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. So I'm counting. This is 6 points, right? 12 points? 12 points out of 12, right? Question number 7. 16.7 kilograms is how many grams? 16.7 kilograms. So they do these conversion things in chemistry. We can do it like this, but it's really just fractions. So 1 gram, well, actually 1,000 grams in 1 kilogram. So when you write this, you have to say to yourself, is 1 gram 1,000 kilograms? No. No, because grams are much smaller than kilograms. So then you'd say, oh, right, it's 1,000 grams per kilogram. So why did I write grams up there and kilograms down there? Because what I'm going to do is I'm going to multiply these across. And when I multiply, I'm going to cancel these units, the kilogram units, because a kilogram over a kilogram is a 1. And so 16.7 times 1,000, it's 16.7 times 10 to the 3. See what I did there? grams. Or you could also say this is 1.67 times 10 to the 4th grams. So notice my answer has sig figs, so we have 3 sig figs. It shouldn't change. The 1000 is significant. We're definitely sure that it's down to 1000.0000 grams per kilogram, but it's 1.67 times 10 to the 4th grams. Question number 8. 560 nanometers is how many meters? So we can do this little conversion table here. And actually, I should be careful here because this was a conversion over here, but it equaled this, right? So this is all going to equal. I leave this space in case I need more conversions. You'll see that in the next question. So 1 nanometer, or there are 1 times 10 to the minus nano. Remember our table up here? 10 to the minus 6, 10 to the minus 9. 10 to the 1 times 10 to the 9 meters is 1 nanometer. So I cancel out these units and I find that 560 nanometers is 560 times 10 to the minus 9th meters. But that's just not quite good yet with sig figs and with scientific notation. So you could say this is 5.6 times 10 to the, does this number get bigger or smaller? It actually gets smaller by 2. So this is 5.6 times 10 to the minus 7 meters. Or check it, 560 nanometers is 0.56 micrometers. Because remember, these are off by, these differ by 1,000. So when you divide that by 1,000, you get micrometers. So a whole bunch of nanometers makes up just a little bit of a micrometer and a really small part of a meter. Oh, I cut that off. Let's get that fixed there. All right, so there we go. Question number 9. 15 years is how many seconds? So let's do our conversion table. 15 years. There are 365 days in a year. Good so far. Years are canceling. There are 24 hours in a day. There are 60 seconds in a minute, and there are 60 minutes in an hour. So there are 3,600. That's 60 times 60 seconds in an hour. All of that should give us the answer. So they said you couldn't use calculators on this, but they didn't say you couldn't use the internet. So hang on just a second. So I typed that into Google. Not technically a calculator, but it is a calculator, of course. I said 15 years is how many seconds into Google. And Google came back and said 15 years is 4.73 times 10 to the 8th. So 4.73 times 10 to the 8th. Notice that that has 3 sig figs. Yeah, you could say we have maybe only 2 sig figs for 15 years. So yeah, let's say it's only 4.7 times 10 to the 8th seconds in 15 years. And if you're being a stickler, the units or the abbreviation, yeah, for seconds is S, not sec, but okay. We won't get stickler right away here. 8.99 times 10 to the 9th seconds is how many years? So let's do this the other way. 8.99 times 10 to the 9th seconds. There are 3,600 seconds in an hour. There are, it's hard to read right there. Let me make that a little clearer. So I'm writing my conversion factors in a logical way so I can cancel things out. So go back to the previous question. Years cancel with years. Days cancel with days. Hours cancel with hours. And I get left over seconds. And the reason why you can do all this is because 24 hours in one day is 1, because 24 hours is 1 day, 1 over 1. 24 hours over 1 day is 1 over 1, but when you're creating, or when you're doing these, keeping track of units means you have to multiply by these conversion factors, and so you basically scale things up or down based on some of these crazy units that we have. Imagine if there was like a metric system for days where 1 day is like 10 hours, each hour is 100 seconds, each month is 10 days, there are 10 months in a year is, you know, crazy, but you know, that's what you could do if you wanted to like give different units to the whole system. Let me erase this stuff here. So we're writing down all the conversions from 8.99 times 10 to the 9th seconds. I basically have the seconds canceling, but now I need to get to hours. There are 24, 1 day is 24 hours. And then, let's see, hours, days now. So there's 1 year. There's 365 days. So I know I'm getting close to the right answer because I have years left over on top, and that's what I need. So I have to do 8.99 divided by 3,600 divided by 24 divided by 365. You know what? I just don't see how you can do these problems without a calculator. So let me go to my calculator here. 8.99. And the way you do this on a calculator is you have to say times 10 to the 9th divided by 3,600 divided by 24 divided by 365. So this is 285 years. And if we wanted to keep the decimal places, it was 285.07. But I only had 3 sig figs in all of this because I had 8.99, so that's 285 years. So basically, unless you get some kind of long life serum, you're not going to live even this long. So 285 years is is how many seconds. Just double checking in Google over here. So 8.99 times 10 to the 9. Cool, got that one right. All right, 2.998 times 10 to the 8th meters per second. 2.998 times 10 to the 8 meters per second is how many kilometers per hour. So we're still going to do this multiplying and dividing piece, but now we have to do two conversions at once. So I have meters, so there are 1 kilometer is 1,000 meters based on our table, and 1 second is 3,600, sorry, 1 hour is 3,600 seconds. So if I put 3,600 seconds up here, and that's 1 hour, then double check that I get meters canceling with meters, seconds canceling with seconds. So I'm left with kilometers per hour. And so all I have to do is multiply and divide. So let's get this calculator up here again. All right. Clear it. Yeah. 2.99. So what I'm showing you also here is how to drive your calculator. We're gonna be using our calculators this year. Let's just not make any bones about that, but let's make sure we know how to put numbers into the calculator. So that's 2.99 10 to the 8th times 3,600. Some big number divided by 1,000. So 1.079. That's thousands, millions. This is billions. So this is billions of miles an hour. Hey, you might recognize that number, 2.99, as the speed of light. So yeah, the speed of light is really fast. And in particular, it's 1 billion kilometers an hour. So 1,079,280,000 kilometers. Oops, kilograms, no. Kilometers per hour. And so putting this in significant digits, because we have 4 significant digits. So this is 1, 2, 3, 4, 5, 6, 7, 8, 9. This is 1.079 times 10 to the 9th kilometers per hour. Okay, next page. So those are worth about 2 points each. Okay. Trigonometry review. What you need to remember about trigonometry is SOHCAHTOA. So the sine is the opposite over the hypotenuse. The cosine is the adjacent over the hypotenuse, and the tangent is the opposite over the adjacent. So if I have an angle here, this side is called the opposite to that angle. This is called the adjacent to that angle, and this is called the hypotenuse of the triangle. So let's write down some of these relationships. The sine of the angle, just a mathematical relationship in a right triangle. Every right triangle with that angle has this ratio of the sides opposite over hypotenuse, A over C. Cosine of the angle theta is B over C, and the tangent of the angle theta is always opposite over adjacent A over B. Find C if you're given A and B. Oh, don't forget Pythagoras. Pythagoras, a Greek geometrician. The hypotenuse squared equals the sum of the two sides squared. So if you're given A and B, C is equal to the square root of A squared plus B squared. Find A if given B and C. So A is equal to the square root of C squared minus B squared. Here's what I did. I pulled the B squared over here because I wanted A by itself. I took the square root. This is definitely a positive number because C is always, the hypotenuse is always the longest leg of the triangle. Actually, it's not the leg, it's the longest side of the triangle. Find A if you're given C and theta. So if I'm given C and theta, C times the sine of theta equals A. Putting boxes around my answers. Find B if given A and theta. B if you're given A and theta, so B is equal to A divided by the tangent of theta. We have a word for 1 over the tangent. It's also called the cotangent. So this is A times the cotangent of theta. Either one of those answers would work. Nice job. Next question. Find C if you're given B and A. Wait, yeah. Okay, so we know that the tangent of theta equals A divided by B, but I want theta. So how do I get it if I've given A and B? So these are the inverse trigonometric functions. So you take the inverse tangent of the tangent of an angle. So you take the inverse tangent of A over B. The tan is undone by the inverse tangent, so this gives you theta equals the inverse tangent of A, B. Oops, I went to 18. Theta equals the inverse tangent of A over B. I get a little sloppy sometimes, so just call me out on that. Find C if you're given B and theta. So C is down here, B and theta. So this is C equals B over the cosine of theta. 1 over the cosine is something called the secant. So this is also the secant of theta times B. I guess get in the other question I wrote it in the more standard order. So this is B times the secant of theta. Find theta if you're given B and C. So here's B, here's C, here's theta. So this is the inverse cosine. So theta equals the inverse cosine of B over C. Notice that this is not called 1 over the cosine. 1 over the cosine is called the secant. This is inverse. So something to the -1. If this here is a trig function, the -1 is notation which means inverse of that trig function. Remember, if I say that 2 squared equals 4, and I say, what do I have to square to get 4? You basically have to take the inverse of the square function, which is called the square root. So basically you learn that 2 equals the square root of 4. Squaring and square root, those are inverse functions. If a is 2 and c is 7, what's b? b is the square root of c squared minus a squared. So 49 minus 4 square root equals the square root of 45. That's not a really easy number, so we can just leave it as the square root of 45. If c is 10 and theta is 60, what is b? Alright, so remember, b and c are related by the cosine. So the cosine of 60 equals b over c, which equals 10. The cosine of 60, I just happen to know, is 1/2. So 1/2 times 10 equals b, which equals 5. You'd be hard-pressed to know that without memorizing some values. So you're okay using a calculator on that one. If a is 12 and theta is 30, what is b? So remember, the tangent of theta equals a over b. So the equation we're using is the tangent of theta equals a over b. So b equals a divided by the tangent of theta, which equals 12 divided by the tangent of 30 degrees. So 30 degrees, the tangent of that is, I think that's the square root of 2 over 2. So if you do 12, alright, let me show you what I'm doing. I'm doing 12 divided by 30 tan equals 20.78. So, writing down all the digits we know, 20 point, well, way more than we think are significant, 28.4609, blah, blah, blah. But we only have 2 sig figs here. We'll assume 30 degrees has 2, so this is 21 equals b. Okay, next page. That was 2021. Okay. Using the properties of triangles, prove that the angle of A is congruent to the angle of C in the drawing below. Hang on just a second. Okay, a couple ways to do this. Let's do one way first. Remember that the sum of all angles in a triangle equals 180 degrees. Remember that two angles are complementary. If they sum to 90 degrees. So this is the definition of complementary angles. And remember that two angles are or a bunch of angles are supplementary if they sum to 180. So remember that let's call this point here D, and let's call this point E. So what I would like you to notice is that the measurement of angle E is equal to 90 degrees, and the measurement of angle D is equal to 90 degrees. That's what this little symbol means, right? Perpendicular. You could say that's the definition of perpendicular or something, right? Then you would have to say that the measure of angle A plus the measure of angle B plus the measure of angle D equals 180. But that's also the same as saying the measure of angle A plus the measure of angle B equals 90 degrees. Are you good? Right? So this angle plus this angle plus this angle have to equal 180. But if that's 90, then these angles just have to add up to 90 themselves. That's what we've said so far. Now let's look at this, what's going on here. What I've got is the measure of angle E plus the measure of angle C plus the measure of angle B equals 180. But remember I said that the measure of angle E is 90, so this means that the measure of angle C plus the measure of angle B equals 90. Alright, so then take a look at these two right here. If the measure of angle A plus the measure of angle B equals 90, I can start writing that right here. But if that equals 90 and this equals 90, then that also means that the measure of angle C plus the measure of angle B equals 90, so those are equal. If by transitive property of equality, if this equals 90 and that equals 90, then they must both equal each other. Now, subtract the measure of angle B from both sides. You see that the measure of angle A must equal the measure of angle C. If two angles are equal, then they are congruent, which is what the symbol means. Then angle A is congruent to angle C. This little proof will come in handy for some problems that we're going to come up against in physics. Okay, so if you remember that the sine of any angle can be written as an expansion. So it's pretty fancy, but it's called the power series expansion, or the Maclaurin series. So let's write this down. I'm going to change the color. I'm getting tired of red. I'm sure you are too. So here we go. So it's something called the Maclaurin series. It's also called the power series for sine. If I say that I want the sine of a quantity x, I can get that by doing x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial. And I think you see the pattern, right? So that it's going to be a plus x to the 9 over 9 factorial. So here's the thing. 9 factorial is getting, well, the factorial numbers are getting bigger and bigger. This is 3 times 2 times 1, so that's 6. This is 5 times 4 times 3 times 2 times 1. So that's 20. 5 times 4 is 20, times 3 is 60, times 2 is 120. So these numbers down here are getting bigger. But also these numbers up here are getting bigger, especially if the number is greater than 1. But here's the thing. The sine of some angles is getting much smaller. So check this out. If this x is less than 1, then these numbers here are getting very small very quickly. So if x is less than 1, then these numbers are getting very small, so the sine of x is approximately equal to x. And in degrees, that's the tricky part. So 360 degrees is 2 pi radians. It turns out this formula is it's true for radians especially. So that means that 1 radian is about how many degrees? Well, we have to do 360 degrees is 2 pi radians. So let's do that with our calculator here. So 360 divided by 2 divided by pi equals 57. So 1 radian is like 57 degrees. So for angles less than 57 degrees, the sine of theta is about equal to theta, let's say. But it's especially true for things that are less than 0.1, right? So for x less than 57 degrees, that's a pretty good approximation if x is less than 57 degrees. Okay. All right, so when you have to do this, so question 24, let me change colors here. When you have to do these calculations of sines and cosines, it helps to have a circle in mind and then start drawing these things out. So if the angle here is 0 or theta, sine is opposite over hypotenuse. A over C B. So when this angle is 0, the A, that distance is actually 0. So sine of 0 is 0. In the unit circle, C equals 1. So the cosine of 0 is 1. Tangent is the sine over the cosine, so the tangent is 0. So let's also do 90 degrees. So if you're up here at 90 degrees, the sine is 1, cosine is 0, the tangent is infinite. Crazy. Because 1 divided by 0, right? 30 degrees. 30 degrees is interesting because 30 degrees is the sine actually is a half at 30 degrees. And the sine of 45 degrees. Here's how I remember the sine of 45 degrees. If you have a 45-degree triangle, ones on each side. Opposite over hypotenuse is 1 over the square root of 2, so this is the square root of 2 over 2. Remember that the sine of the angle is 1 over the square root of 2, but we don't leave the square root of 2 on the bottom, so you multiply top and bottom by the square root of 2. Square root of 2 times the square root of 2 is 2. The square root of 2 times 1 is 1. So that's also equal to the cosine, because the cosine and the sine are equal at 45 degrees, and the tan is 1. So that's cool. The cosine of 60 degrees is actually 0.5. And the tan is the sine over the cosine. So hang on, we'll get to that in a second. The cosine of 30 degrees, I forget this one, but we're going to have to memorize it. So 30 degrees cosine. Okay, so this is the cosine of 30 degrees is the square root of 3 over 2. And the tan is the sine over the cosine. So what's 1/2 divided by the square root of 3 over 2? Well, that's 1 over the square root of 3, square root of 3 over 3. That means that the sine is the square root of 3 over 2. And the tan is square root of 3. And the tan of 30 . All right. So that's the table. You know, some of these are easy to remember, some aren't so easy to remember. I can teach you some tricks sometime about those. But you're welcome to use, you're welcome to use the internet instead of a calculator. On the AP test, we'll give you a table of these values. So, you know how it usually works in math classes, right? We tell you to remember stuff if we think it'll speed you up at some point. And the way you speed yourself up is by doing it over and over again. So, okay, fine. So 360 degrees is 2 pi radians, because that's how you define a circle is 2 pi, and 360 degrees is all the way. So 4.5 revolutions. So 4.5 revolutions if there are 2 pi radians per revolution, then this is basically 9 pi radians. So we're just playing with different ways to measure how far you're going around a circle. The length of an arc, the length of the arc is the radius times the angles in the arc in radians. So if I have the length of the arc is 6 meters times 2.5 radians, then I have basically 2 times 6 is 12, 3, 15, right? 15 meters. And then 10 meters, S equals 10 meters times 100 degrees, but there are 2 pi radians in 360 degrees. So that's 10 meters times 100 times 2 pi divided by 60. So let's just crank this out. 10 times 100 times 2 divided by 360. So that's 5.555 times pi 5. 5.5 times pi meters. You can see I'm leaving the pi in there. I could do that, or I could actually figure it out. So let's multiply by pi. $17.45. We have 3 significant digits. So remember, pi is about 3.14, so 3 times 5 is 15. 3 times 5 is 15, 16.5 or so 17.5. Makes good sense. Okay, next. We've got some equations, and we'd like to solve for the given variable. So if v1 plus v2 equals 0, then v1 equals negative v2, because you just subtract v2 from both sides. If a is v over t, then t equals v over a. The steps for that are multiply both sides by t, divide both sides by a. You'll get to there. Vf squared equals vi squared plus 2ad. Solve for vi. So vi, I know I'm going to have a square root in there at some point, but I know I needed to take 2ad and put it on the other side, and then take the square root. So I do these really fast, and you should get so that you can do them pretty quickly. And solve for d from this equation. Vf squared minus vi squared over 2a equals d. I also know that these are coming from the kinematic equations in physics, so I kind of used to these solutions too. So what I did, I subtracted vi squared from both sides. I divided by 2a on both sides, and then I got d. If df equals di plus v0 t plus a half at squared, solve for v0. v0 equals df minus di minus 1/2 a t squared divided by t. Right, because we had a t times v0 that we had to divide by. In my head, I'm basically getting everything on the other side of the equation. And then I'm getting, so solve for t if v0 equals 0. Df equals, let me work it out in detail, plus 1/2 a t squared. If v0 equals 0, this is 0, so it's df minus di times 2 divided by a square root. Alright, so solve for t if df equals di. If df equals di, let's write it out. Df equals di plus v0t plus 1/2 at squared. Df equals di there cancel because you could subtract or add or something. So now I have, well, 0 equals v0t plus 1/2 at squared. So when you're trying to factor things for 0 or figure out what makes this equation 0, 0 equals t times v0 plus 1/2 at. So it equals 0. T could be 0, or it could be equal to v0 plus 1/2 at could equal 0. So that means t could equal minus v0 times 2 all over t, all over a, sorry. So t equals 0 or t equals minus 2v0 over a. And, you know, I might come back to these equations later, but we're going to use them or derive them or find them out again in this class. All right. If ti equals 0, find the final velocity, vf. So let's get a different color. Maybe it's time for purple. Force equal F equals m times vf minus vi over tf minus ti. Solve for vf. F over m times tf plus vi equals vf. That was a lot of steps at once. Here's how I walk through it. Divide both sides by m, you're good. F over m, multiply both sides by tf, cancels out over here, f over m times tf. Add vi on both sides, you're left with vf. If both vf and ti equals 0, f equals m v minus vi all over tf TF equals minus MVI all over F. So I basically brought the TF up, multiply both sides by TF, and then divide both sides by F. V equals AC times R square root. So you have to multiply both sides by R, and then take the square root of both sides to get V by itself. Mg sine theta equals mu mg cosine theta. M's cancel, G's cancel. Sine of theta over the cosine of theta equals mu, but the sine of theta over the cosine of theta equals the tangent of theta equals mu. Theta equals the inverse tangent of mu. Solve for h of f if h of I equals 0 and vf equals 0. If hi equals 0, this whole thing is 0. If vf equals 0, this whole thing is 0. M's cancel either way. H of f, divide both sides by g, vi squared all over 2g. Solve for vf if hf equals 0. Let's write the whole thing out again because I kind of messed it up by crossing stuff out on the last one. M's cancel. H of f equals 0. Vf equals, remember we got a square root, vi squared plus 2ghi. Is that okay? I just had to stare at it. So you have to multiply 2 through here. The 2 cancels there, but there's a 2ghi. Vi squared plus 2ghi square root vf. Ft over m equals vf minus v. Add v to both sides plus v equals the vf. Remember, when you divide both sides by m, there's an m still over here in the bottom. Then you can just add the v and get the final velocity. M1 times vi comma 1, vi comma 2. Vi comma 2 is right here. How do you get that by itself? Vi comma 2 equals m1 plus m2 times vf minus m1 vi comma 1 all over m2. Take a minute to stare at that. I'm basically recalling that the V's are different if they have different kind of subscripts on them. But the masses just move around. Yeah. Solve for VF2 if VI1 equals 0. VI1 equals 0, that's gone. M2 VI comma 2 minus, I got kind of sloppy, hang on a second. M2 VI comma 2. Let's subtract this M1 VF1. Divide that by M2. That leaves you with just VF comma 2. So we're just rearranging equations there. Sorry that they don't seem to make much sense right now. They will make sense at some point in AP Physics. Solve for R2. F1 times the sine of theta. Now I added that all to one side, so just divide by F2 times the sine of this. This symbol is called phi equals R2. Oops, there was an R1 here. R1 F1 sine theta. You added, so that was negative, so you add it to the other side, then divide F2 times the sine of phi. You could write this equation as minus kx equals gm, right? M times negative g added to both sides. So that means that m equals minus kx all over g. That looks kind of scary because m looks like it's negative, but k or x could be negative too, right? Alright, solving for r. You might recognize this equation as the gravity equation. So r equals g, divide both sides by f, and multiply both sides by r squared, then take the square root. So r equals the square root of gm1 m2 all over f. That's not f times g, by the way. That's just a subscript g. So let me be a little bit neater about that. That's f of g. Solve for L. If you factor out L, you get 1 minus the cosine of theta equals v squared over 2. So really L is equal to v squared over 2 times 1 minus the cosine of theta. Getting kind of sloppy here. V squared. Okay. mv squared over r equals gm big M little m over r squared. So, hey, watch this. The m's cancel. Bonk, bonk. And one of these r's cancels. So v equals the square root of g, big M, big R. Okay, solve for g. T equals 2 pi times the square root of L over g. You have to square both sides, so t squared equals 4 pi squared times L over g. G equals 4 pi squared L all over t squared. I'm going to put my box around the answers here. If VF equals 0, solve for x. This whole thing is 0. Multiply by 2 on both sides, so k x squared. Kx squared equals mvi squared. I'm multiplying by 2. I divide both sides by k, and then take the square root. It's not hi like high, it's h sub I, subscript. And then take the square root. All right. One over RT equals 1 over R1 plus 1 over R2. So, RT let's get a different color. Alright. Brown. What I did is I did 1 over on both sides. So I divided both sides by 1. So 1 divided by 1 over RT, multiply top and bottom by RT, you get, these cancel, you get RT. So that's how I get RT by itself. But 1 over that just says put it all under 1 over. And actually, it doesn't really simplify all that much. In other words, you can get this to multiply top and bottom by R1 times R2. R1 times R2 equals R2 plus R1. That equals RT. That's about as reduced as you can get it. But some people like this better because R1 and R2 only show up once in either spot. So, okay. Now let's make sure we understand fractions. If I multiply this one by 6 24ths plus 4 24ths, then I'll get 10 24ths, or I'll get 5 12ths. I think you could have seen that 12 would have been an easier way. Multiply that one by 3 over 3 and this over 2 over 2. You get 12 on the bottom both sides, so you get 5 on the top. Those equal signs aren't real clear. Let me clean them up a little. Okay. This one, you know, I can multiply this one by 6 over 6, so I get 6 over 18 plus 1 over 18 equals 7 over 18. I can't really reduce that. All right. As x increases, so z equals x over y. As x increases and y stays constant, z increases. As y increases but x stays constant, z decreases. If you have trouble with these, just put in some numbers, right? So if z equals 2 over 2 or 3 over 2 or 4 over 2, that's basically z's increasing, right? 1, 1.5, 2. Anyway. All right, as x increases and z stays the same, y. So you really need to basically rewrite the equation. Y increases. C equals A times B. As A increases and C stays constant, B equals C divided by A. As C increases and B stays constant, A increases. Here's how I did that. I basically said A equals C divided by B. So as C increases and B stays constant, A has to increase here, right? If B increases and A stays constant, then C increases. That's the original equation, right? C equals A times B. If B increases and A stays constant, then C increases. L equals M minus N. M Sometimes I like to do my L's kind of loopy like that so I can see them better. Otherwise it looks like a 1 or something. L equals, so M equals L plus N. L increases, N stays constant, M increases. R equals S squared over T squared. If S is tripled and T stays constant, R is multiplied by. So let's see here. R prime, or R asterisk equals 3 times S squared all over T squared. R equals 9S squared over T squared. So R is 9 times little r. R star is 9 times little r, because remember, S squared over T squared was little r. R is multiplied by 9. if t is doubled, r is s squared over t squared. R star is s squared all over 2t squared. That equals 1/4 s squared over t squared. So that's 1/4 times r. R is multiplied by 1/4. The new r is 1/4 of the old r. All right. I've kind of forgotten to put points on these. We'll see where we wind up. All right, so we got, I think we've got this page and then the next page, then we're done. Okay, not quite. How many equations are needed to solve for one unknown variable? Usually the number, so let's see here. The number of equations that you need is equal to the number of unknowns. The number of equations you need is equal to the number of unknowns. So if you have one unknown variable, you need one equation. For two, you need two equations. Two unknowns for three equations. Sorry, for three unknowns, you need three equations. So if f sub f equals mu times f sub n, solve for mu, f sub f all over mg cosine theta equals mu. Right, because this all down here was f sub n. So f sub f divided by mg cosine of theta is equal to mu. Scratching my head. f1 plus f2 equals f sub t. F of 2 equals f1 d1 all over all over d2